there. Okay, so everybody, I've started recording. So let's take a look at the chain rule. So I'm going to throw some stuff out. So here, something nice and easy. Let's say we have y equals x to the 4. We know how to take the derivative for x cubed. It's one of our, basic derivative rules. If you have y equals sine x, we know that, oops, sorry, that's y prime. Y prime is equal to cos x. Okay? These are our basic derivatives. Now, if I had, say, y equals x minus 1 squared, and I wanted to find the derivative, okay, I could first expand this, okay, and then take the derivative. Nice and easy, okay? This is where the problem comes in. What if I have y equals x minus 1 to the, 14? Can we all agree that we do not want to multiply that out 14 times? Okay, it starts to become, and what if instead of being x squared minus 1, it's even worse? What if it's, 3x squared plus 7x plus root x all to the 14? It doesn't make sense to multiply this out. You could, but you certainly didn't want to. But it gets worse. What if I have even something like sine of x squared? Okay, I don't have any trig identity that allows me to rewrite this nicely in a way that I could take the derivative using these simple derivatives. Okay, so this is where we have to come up with another rule. So everybody remembers you got the product rule. Okay. I think this was the last thing I did when I was here last time. Okay. You have the quotient rule. So when you're combining functions that are made up of a quotient to two functions, you have the quotient rule. Well, now the next level, okay, that really helps you take almost any derivative you want is what's called the chain rule, okay? And so this is what we'll review now, and we'll do some examples, all right? In fact, let's take the example of y equals x squared, okay? So, sorry, sine of x squared. Y equals sine of x squared. Now, this in itself is not too simple a function, but can somebody tell me what two simpler functions we see? Okay, what are two simple functions that we see here? Can anybody tell me? There's two simpler functions hiding here. There you go. We see that there's the function y equals sine x. Now I say simple because we know how to take the derivative of sine x. And we also have the function x squared. Okay. So what would be really good is if we could find a way to take the derivative of this more complex function using the derivatives of these simple functions. And that's what the chain rule allows you to do. Okay. All right, so let's see how the chain rule works. And the chain rule works by multiplying the derivatives of these simpler functions. But we have to do it in a very clever way. And the way we do it is we always start. Normally, when you have brackets, you start inside and then you move outwards. When we're using the chain rule, you always start with the outside function and then you move to the inside function. Okay? And this is how the chain rule works. Is this function inside the brackets, you forget that it's a function, okay? You just think of it as some variable. And the variable we often use to represent that is u, okay? And then you're going to take the derivative of the inside function, which is just x squared, okay? So think of this outside function, sine, it's just sine of a, variable. What's the derivative of sine u? Just cos u. And then what's the derivative of the inside function, okay, the derivative of x squared is just 2x. And let's see how that would work, okay? So if I want to take the derivative here, and often I don't write this step, but let's write it out, okay? We're going to take the derivative of sine u, and now since my variable is u, it's going to be with respect to the variable u. And then I'm going to multiply that by the derivative of the inside function, and the inside function is x squared. So derivative of x squared, since my variable is x, it's d over dx. Okay, so let's see what happens here. What's the derivative of sine u? This is the one we all know. What's the derivative of sine?
Cos u.
There you go. It's just cosine of u. Okay, times, well, the derivative of x squared with respect to x. That's easy. I'm not even going to bother asking. Is 2x. And this now represents the derivative of this function. But of course, I don't want u in my final answer. But let's remember, what was u representing in my original function? U was just representing that inside function x squared. So when you give your final answer, you're going to give it as cos of x squared and then times 2x. And there's your derivative, okay? And once you get used to using the chain rule, you're not going to bother writing these first two steps. You're going to go straight to this step here, okay? But the way you want to think about it, and sometimes it's actually not a bad idea to sort of hide the inside function. You just say, oh, what's the derivative of the outside function? The derivative of sine is cos, but not cos of x. What's the input to that original function sine? It's x squared. So cos of x squared. And then you take the derivative of the inside function, which is just 2x. Okay, so looks like I have a, hold on, I just, okay, Manal, you got your hand up?
Yes, teacher. Actually, I have a problem understanding the idea of derivative of something over something. Can you just explain it? Because things got mixed up with me when it started with dx and du. Is it okay with that?
Yeah, okay, so let's go back here. And the reason, so are you talking about like finding the derivative when there's a quotient? Is that what you're asking about? Or are you talking about what I wrote here?
What you wrote here, because this idea, I don't understand it.
Yeah.
Even if
Now,
I saw it in a YouTube video, I
yeah,
cannot understand it.
yeah. And so here, unfortunately, showing you why this works is just, it's beyond this course. So like last time when I did the product rule, I was able to show you why the product rule works. Unfortunately for the chain rule, it's just that the proof of that is a bit beyond the course. So it's hard to really show you sort of, why it works, but I'll give you an example here. Okay.
At least, how can I understand it?
Yeah.
Just how to understand it.
So the idea is that when you're taking the derivative of this outside function, okay, what's the input to that outside function? Can you see that it's not just x, it's just not the variable itself? It's something more complex than just the variable. It's x squared.
Yes. Yes.
Yeah. So this is the idea of saying, you know what? For taking the derivative of the outside function, I'm just going to call this inside function, I'm just going to give it a name. I'm just going to call it the variable u. Okay? Okay, so u is kind of replacing x squared. Okay? But now when I look at that outside function, I have now something that I know how to take the derivative of. Okay? Now, when I write d over dx of x cubed, say, what is this representing? This is not a fraction. It's just representing that I'm taking the derivative of a function, and what this tells me is that the variable of my function is x. And we see here, what's the variable in the function? It's x. So the symbol we use to take the derivative when the variable is x would be d over dx. Let's say I was taking the derivative of, my function is not given in terms of x. Let's say it's a function that has time. So I'm using t, and I have t cubed. Well, what symbol would represent taking the derivative of t cubed? It wouldn't be d over dx. What's the variable now?
dt.
There you go, d over dt. So it all depends on what the variable of your function is. So here, if my function was in terms of, I don't know, what else do you have in functions? Let's say it's a big T for temperature, and you want to find the rate of change of the temperature. What would I use as my symbol to represent the derivative of the temperature? It would be d over d capital T.
Capital T.
So that's what this variable in the denominator represents. It's just whatever the variable of your function is. So here, if I'm replacing the x squared, whatever that inside function is, whether it's x squared, whether it's e to the x, whether it's x cubed, regardless of what it is, if I'm going to replace that by u, when I want to write that I'm taking the derivative of this function, I have to now use the variable of that function. So that's why we write d over du. Because now what's the variable inside my function?
It is you.
Not x, it's u. That's why I write it. Okay.
Mm.
Now, when I take the derivative of the inside function, well, the inside function is again a function of x. So that's why in the second part of the chain rule, I write d over dx, because now the thing I'm taking the derivative of is a function of x. All right?
Yeah.
Does that give you a bit more? So now let's do them one at a time. Now this is a simple function because I know how to take the derivative of sine of just the variable, not the variable squared, not the variable times 7, not anything like that. I know that the derivative of sine of u, okay, if it was sine of x, it would be cos x. If it was sine of t, it would be cos t. Since it's sine of u, what's the derivative? Cos
Yeah.
u.
Mm.
And now I take the derivative of the second one, which is easy, 2x. But you see how when I want to give my final answer, u doesn't appear in my original function. I'd like to only see x's in my final answer. So what was u representing when I brought it up? It was just representing x squared. So that's why I can now replace u, replace it back with what it was representing, which is x squared. Okay.
Thank you.
So maybe let's do another example and let's see how it goes. Okay. So let's take, I'll do 2 more examples and then I'll give you maybe a few to work on. Or actually, you know what? Before I do that, I guess I better take attendance here. Okay, so, oh, there's my clock telling me to take attendance. Let me just get my attendance thing here. So I think it's already in order. So I just want to check. I'm going to say the names out just in case I don't see you or there's a different name. So I'm just going to read them out, but I'll also check while I'm looking. Okay, so Awan Abbas. No. Okay. Kyle Algu. No. Okay. Sorab Ali, I see is here.
Here, sir.
Yeah. Dardan Asani. No. Elijah Borges, I see. Galiba Barnona.
Here.
No. Oh, you're there. Oh, okay. You show up a different on the list. Okay, perfect. Okay, so you're here. Queenie Chan, I think I saw. Yes. Ting Ting Chen is here.
Yes.
Hatis April Dinger.
I'm here, sir.
Very good.
I'm here.
Okay. Colin Draper. I see. Yeah. Okay. Hamda Farah. I see.
Here.
Yeah. Roya Gulam Alaya. I see. Good. Let's see. Ahmed Hassan.
Hamadi,
Hamani. Sorry, I was looking up.
Yeah,
I
yes, sir.
was looking where. Yeah. Oh, here we go. Ahmed Hamani is here. Hamadi. Sorry. Najib Hersi. I see. Very good. Ruben Hong. I see. Jamila Husseini. Oh, I see Jamila. You here? Is that Jamila Husseini who I see?
Yeah.
Yeah, perfect. Okay. Stanislaw Jakowski, I see. Jenny
I'm here.
Lee, I can see. Perfect. Ambry Mahesan. Is Ambry here?
Here.
Okay, perfect. Philip Mihalovsky is here. Okay. Mariana Mohammed. Is Mariana Mohammed here? No, okay. Yusra Mohammed. Is Yusra here? Roya Ghulam Ali. Yes, I did. I saw you on the list. So some of you are appearing in the right order, but for some reason, some of you are not. Yusra Mohammed? No. Okay. Shu Mayo or Mio?
I'm here.
Perfect. Okay. Cole Pearson.
I'm here.
Okay, good. Okay, Sinisa Pejovic. Sinisa, no. All right. Jalen Phillips, I see on my list. Yeah, you're here.
Yeah, I'm here.
Yeah. Goduli Pora. Oh yeah, I can see that.
Yeah, I'm here.
Perfect. Maxwell Pempe looks like here. Oh, Prempe, sorry, is here. Okay, Vikram Roy. I don't see him. Is Vikram Roy here? No. Okay, Khadija Safula. Is Khadija here? No. Okay. Luke Santos. Yeah, I see Luke Santos is here. Samia Sarah. Yes, is here. Zoe
Yes, here.
Sarjanis is
I'm
here.
here.
Perfect. Kauser Shakil is here.
I'm here.
Wow, this is a big class. Dukajan Shala. Dukajan? No. Okay. Ahmed Sumro is here. Ariel Stanisha is here. Okay, I see. Fazi
Yeah.
Sayed is here.
I'm here, sir.
Good. Manal Tartusi is here.
Yes, teacher.
Perfect. Faiza Tasmin, I don't see on the list. Is Faiza here? Faiza, no. And Nina Tverdonova. Is Nina here? No. Okay. So give me just a second. I have to send this off. Okay, phew, that's such an ordeal to take attendance. All right. All right, so should we do another, do you want me to do another example? Okay, let me pick something here. Here, let me take y equals, let's use an exponential function, e to the x cubed plus 3x. Okay, now, can you see here how there's two easy functions? Okay, the inside function is x cubed plus 3x. Okay, and what's the outside function? Well, it's just e to the x. But since I don't have e to the x, who's going to tell me what I'm going to call this inside function to help me determine the derivative? Okay, I'm just going to call this my u again. Okay, so now I'm going to try to do this without writing all these other steps. I'm going to talk it through. And if there's something you're not understanding in what I'm saying, I need you to stop me. Okay, please, everybody promise me you're going to stop me. So I'm going to talk it through. And this is the conversation you should be having in your head when you're trying to do this derivative. Okay. The outside function is e to the u. Forget what this whole thing is. Just think of this as e to the u. What's the derivative of e to the u? Oh, just e to the u. Okay. Then times, forget what the outside function is and just look at the inside function. What's the derivative of x cubed plus 3x? It's just 3x squared plus 3. And now, do I want to see this u hanging around? No. So I just replace it by what it's representing. So e to the x cubed plus 3x times 3x squared plus 3. Okay. Now I'm going to do one more example, but you see, I'm not even going to write this step at all. I'm going to go straight from here all the way to there, because the whole point is to eventually be able to do the chain rule one step without having to write all the details. So now,
So
yeah,
teacher, can you make an example with E minus U?
e to the negative u?
Yeah.
Yeah, okay, let's take that one. In fact, that one's even easier, but do you know what the funny thing is? Is people are more likely to make a mistake on this one than to make a mistake on that one, okay?
Okay.
And the reason is it looks so simple. Oh, instead of x, it's just negative x. Ah, but is this e to the x? And the
It
answer
is,
is no.
yeah,
It's e
1
to
over
the
EX.
negative x. You know what? No, I do not want to I don't want to write it as a fraction. That's more work than this is how I want to write it. It's
Oh,
easy. Yes, it's
okay.
easier to solve this with the chain rule than with the quotient rule. The quotient rule, look how quick this is going to be. As soon as I see I have anything other than just x, as soon as it's negative x, this becomes my u. This negative x becomes my u. So again, remember we said, forget what is there. What's the derivative of e to the u? E to the u. It's the simplest
to U.
derivative. There you go. Now I'm going to skip writing that second step because in my head I go, oh, e to the u. Well, yeah, u is just equal to negative x. So there you go, e to the negative x. But what people forget sometimes is that now I have to take the derivative of the inside function. So what is the derivative of negative x?
-1.
There you go. And so the derivative is just going to be negative e to the negative x. Okay. And sometimes because it's almost x, it's just negative x, people forget to take the derivative of that inside function. Okay. They rarely forget it here because it's very, very obvious. You see it, you know you have to take the derivative of x cubed plus 3x. Make sure you don't make the mistake when it's simpler to forget to take that derivative. Okay. And this is how the chain rule works. So should I give you a couple of examples to work on?
But teacher, at the end, can I write it in a fraction way or keep it like
Oh
that?
yeah, at the end, if you want to rewrite this now, you can rewrite this as -1 over e to the x,
Okay.
over e to the x. Sure, you can. But very often you're taking derivatives to then solve problems. And it's often easier to just have this in the numerator than it is to have it in the denominator. So certainly this is even in some ways the nicer way of writing it. But, remember, we don't take derivatives just to take derivatives. We're going to be taking derivatives eventually to solve problems. And very often it's easier to work with things in the numerator than it is to work with them in the denominator. Okay? But for sure, this is perfectly fine. Okay, let me just give a couple of examples and then I think we should move on if we have time at the end, if people have specific stuff they want to ask. So here, let's write it in function form. So let's say I'll give you here. And if you want, I can give you one that's a little more interesting here, okay? We're going to do e to the square root of x squared plus 1, okay? This one's a little more interesting, okay? So let me give you a couple of minutes to work on this, okay? If you have any questions you want to ask in the chat, I haven't looked at the chat in a while. Okay. Okay, so let me give you a bit of time. So see if you can follow these examples here. I'll even show the one at the top here. See if you can follow these examples to work on that. All right. Let me know if you have any questions. Yeah, I know that's looking good for the first one. Okay, so if people want to check their answer for the first one, you can look. I'll take it up real quickly, but if you want to look on the chat, that is correct. Okay, we'll go 2 more minutes to try to at least finish the second one, but if you can do the third one, that's great. So let's wait a second. Don't put the answer in the chat yet, just so that everybody has a chance to finish it, okay? Okay. So let's take a look at these here. So if we look at, I'll do it, this is going to be a little long. And again, what I want you to do is I want you to listen to how I'm doing this, okay? And when you're taking these derivatives, the best way to avoid mistakes and doing them too correctly is to literally have this conversation in your head while you're doing it. So when I look at this here, I'm seeing u to the 50. What's the derivative of u to the 50? It's 50 u, which is this whole thing, all to the 49. So 50 u to the 49. And then I multiply that by the derivative of the inside function, and that one's nice and easy. Just 3x squared plus 6x plus 5. Okay? Now, I'm looking at the answer that was given there. Looks good. Now, what would be helpful to solve this derivative? Well, it's to first rewrite root of cos x as cos x to the 1/2. Okay, we know that that's always helpful when you're taking derivatives. Since you're going to use that power rule, it's nice to rewrite this as a power. Okay, so let's take the derivative here and see if I get the same answer as is on the chat. Okay, so again, here, I just think of this as u. What's the derivative of u to the 1/2? It's 1/2 u to the negative 1/2. Okay, so that's the derivative of the outside function. And now I multiply it by the derivative of the inside function. And the derivative of cos x is just negative sine x. Okay? And there you go. And you start to see that there's, you get used to this idea of, hiding the inside function. Just think of the outside function, okay? And then think just the derivative of the inside function. Okay? So now let's take a look at the next one here. And this one's very, very interesting because how many times do I have to use the chain rule here? Can anybody see that I need to use the chain rule more than once? Because I need to use the chain rule when I find e to the u, okay? But then when I take the derivative of x squared plus 1 to the 1/2, I have to use the chain rule a second time, okay? So the first thing I'm going to do, like I said, to help me out is e to the Let me rewrite this as x squared plus 1 to the 1/2. Okay. And now let me take the derivative of this function h and look at what I do. And the trick to doing this correctly is to just take it one at a time. Don't try to do this too quickly. Okay. So here, forget all the stuff that's going on there. All I care about is the derivative of the outside function. So this whole thing is my u. And so what's the derivative of e to the u? Just e to the u. So e to the x squared plus 1 to the 1/2. Okay, that's the first part, times. Now I have to take the derivative of the inside function. But can you see that I have to use the chain rule to take the derivative of the inside function? So I'm going to forget this x squared plus 1, and I'm just going to think about it. Well, I've used u already, so let's call this maybe v. Okay, and I have to take the derivative of v to the 1/2, which is 1/2 v to the negative 1/2. That's the second function. And now finally, I can take the derivative of the inside of that function. And what's the derivative of x squared plus 1? 2x. Okay. So this whole big thing, but this is why we call it the chain rule, because each function, it's like connected like links in a chain by multiplications. This is the derivative of the outermost function, e to the u. Then you're taking the derivative of the second outermost function, the v to the 1/2. And then you multiply by the derivative of the innermost function. And sometimes you could take, I could give examples, like when I give there's always a question on my tests for my students where there's a question where they have to use the chain rule like 6 times in one shot. Okay. But if you don't think about what the end result is going to be, and you just figure it's like, oh, I know how to take the derivative of e to the x, that's easy. Oh, I know how to take the derivative of x to the 1/2, that's easy. Oh, I know how to take the derivative of x squared plus 1. It's all a series of easy derivatives, okay? So I'm going to suggest we move on. Okay, but definitely practice using the chain rule, please. It's going to come up all the time. So make sure, and especially if you're, if you're taking this course as a prerequisite to, any kind of science university program, you're going to be taking derivatives all the time, and the chain rule is the most important in some ways of the rules. Okay.
Can you give us another example like hx, teacher?
You want to do another example?
Like hx, please.
Sorry, so like what?
The function hx.
Oh, another one. So a harder one? Yeah, let me give you another one here. All right, so let's think up something here. I'll call this one f of x. Oh, let's see. Let's do sine of e to the cos x. There we go. You have to use it a couple of times. Okay, so why don't you give that a try? Okay, so I'll give you about, so don't, if you get the answer quickly, don't put it in the chat right away. Let's give everybody a couple of minutes to try to solve it on their own. Okay, I'll come back in a minute and we'll take it up. Okay, so let's take a look at this one here. Okay, so let's find the derivative. And again, if you see this as a series of easy functions, the chain rule starts becoming a lot more manageable. So forget about what's in the bracket. The only thing I'm looking at is I'm finding the derivative of sine u. And what's the derivative of sine u?
Cosine u.
Exactly. So cosine of, and now I know this whole thing represents u, e to the cos x. You see how each time I'm writing a little less as you get more comfortable doing this. So times, that's the outside function. Now, let's go to the next function. Oh, I'm going to have to use the chain rule a second time. So now, I don't forget about the fact that in the exponent it's cos x. I'm just going to think of this as e to the v. What's the derivative of e to the power v?
Same.
E to the power v. There you go.
Yeah.
E to the power, and we know that the v here is just cos x. And then finally, let's multiply. We get to the last function, the derivative of cos x. Well, that we know nice and easy is just negative sine x. Okay. All right. So thing I just maybe think it would be good, I did a recap based on what you folks told me, is you're starting to see now that the derivative gives you rate of change, tells you how quickly something's growing. So, if I have, f at x equals, x cubed plus x, okay, I find the derivative. But what does the derivative gives me? It gives me the rate of change at a particular x value. So if I take f prime at, say, 1, okay, what do I get? 3 times 1 squared plus 1, so 3 plus 1 is 4. What does this represent? F prime at 1. Who's going to remind me what that represents?
Instantaneous rate.
Yeah. So that's in terms of rate of change. What about on a graph? What does it represent? If I'm thinking of this function, what does it represent on a graph?
Perhaps slope of a tangent.
Exactly. So what this is telling me is that, at, whatever this function is, that at x equals 1, the slope of the tangent is equal to 4. Okay. And if you want to think in terms of rate of change, so let's say this is distance over time, it's telling you that at that moment in time, the object is moving at 4 meters per second, say. Okay. Now, then you start to notice, well, wait a minute, the tangent has a positive slope. So when you have a positive slope, what does that tell you about a function? What's special about this tangent? If the slope is positive, there you go, it's increasing. And then you look at at a point here and you realize that when, whatever it happens to be, you realize that you're going to have that at that moment in time, the function is decreasing. Okay. And then you probably saw that, hey, wait a minute. That means that the slope of the derivative can help me determine the slope of the tangent at any point, but it could actually give me more information. It could tell me any time that the function is increasing or when it's decreasing. So what would happen at each of these points, given that the function is increasing? What do we know about the derivative of all these points because the function is increasing? What can you tell me about the derivative at each one of these points in this interval? It's positive. And then you realize, oh, wait a minute, that means that wherever the function is decreasing, the derivative must be negative. And so this is how you can determine when a function is increasing or decreasing. Okay. Now, why is that important? Well, if I want to sketch the curve of the graph, it's helpful information to know when it's going up or when it's going down. Or more importantly, I mean, whatever job you have, you're probably not going to be using calculus to sketch the graphs. But what you are going to be interested in is, well, when is the you might be interested in when is my stock value increasing or when is it decreasing? When is the amount of carbon dioxide that's being emitted from my machine? When is it increasing or when is it decreasing? Okay, so it's one of the important things we want to know about when something's getting bigger. Yeah, there you go. First derivative tells us when something's increasing or decreasing. Exactly. Okay. Yeah, so we'll look at the second derivative a little later on. Okay, so we're all okay with this, that f prime of x being positive, okay, on some interval. Okay, so this is just, do we know this notation? The x value is going from a to b. Is this familiar to you? I don't want to use something if you don't use it. This just means if my x value starts at a and ends at b, just means all the points between a and b. Is that familiar? Yes or no? Yeah, okay, perfect. I don't want to use something if you guys don't use it. Okay. Okay. So if it's positive, that means f is increasing on this interval. And if f prime at x is decreasing on the interval, sorry, if the derivative is negative, that means f is decreasing on that interval. Okay. So there you go. Derivative, check, gives us increasing or decreasing. Now, what's the other thing we're interested in when we're trying to either graph a function, or let's say the function is telling us how much carbon dioxide our machine is producing. What's the other thing we might be interested in besides just whether it's going up or whether it's going down? And this likely would have been the second thing you taught, the next thing you talked about. What do you think would be interesting to me on this graph? Well, one thing that might be interesting to you is what is the maximum point that you might have on a graph? And of course, if you're interested in the maximum point, you might also be interested in the minimum point. Okay. And so that's the next thing that derivatives help you determine. They help you determine what we call the local maxima and local minimum. Okay. So the first thing, let me redraw this graph. If I have a local maximum and a local minimum, is there something interesting you notice about the derivative at those points? So look at the shape. There should be something very interesting about the derivatives at those points.
It's equal to 0.
There you go. If you try to draw a tangent, I realize, hey, look at that. The tangent has a slope of 0. I have a horizontal tangent, and same thing here. So you start to realize that where you have these maxes and mins, your tangent is going to be 0 there. So that kind of tells you where to look for your maximum and minimum. And there's something else that's interesting about maximum. What's happening with the function before a maximum? What do we notice? How does the function behave before the maximum? It
Increasing.
increases. And then what happens? Then it decreases. But hey, didn't we just talk about increasing or decreasing? So if you want to look for your maximums, you want to look for where your derivative is 0, but you also need to look for where your function changes from increasing to decreasing. And then if you look at the minimum, well, isn't that similar? Except now your function goes from decreasing to increasing. Okay. And so these are very important points. So there you go. Now, here's a question for you. If the derivative is 0, do you definitely have either a maximum or a minimum? Let's do who's good at doing the polls? Somebody last time was doing a poll. Can you set that up? So I want to know what people think. Does having a derivative is 0 mean you have to have either a maximum or a minimum? I guess I can do that, right? So, oh, not necessarily. Do people agree with that? Okay. Oh, yes, no, we're not sure. Anybody else? Okay. Oh, thank you. You're setting up. Okay. So no, not necessarily. Anybody think it does? Oh, lots of other people here. Come on, folks, vote. What do we think? No. All right. Okay. I guess you're not falling for the trap. I was trying to trick you here. Can anybody think of a function? It's a function you all know very well, where the derivative is 0 at a point, but there's no maximum or minimum. Can you think of a function that has that property? Linear. Well, linear function, I guess if it's a horizontal line, you know, there you go, constant, yeah. Oh, interesting, a cubic. There's another example. If you look at a cubic, you see at 0, the derivative is 0, but there's no local maximum or minimum. And that's when you realize, oh, wait a minute. Wait, don't. We're not there yet. We're not there yet. We're going to talk about other things later on. Let's go one step at a time. What do we notice though? The function is increasing, but then what happens after 0? It keeps increasing, okay? And we know that that's a possibility. There's nothing that says that if you start increasing that you have to then be decreasing, okay? So did they call this the first derivative test when you guys did maximum and minimum? Anybody recognize that expression, first derivative test?
Yes.
Okay, so let's recall what the first derivative test is. Okay, so the first derivative test says that if the derivative at some point, let's call it A, is equal to 0, okay? We know that that's where we're going to look for our local extrema, okay? But something else has to happen in order for there to be, let's say, a local maximum. So we're going to say, and if the derivative changes from positive to negative at x equals a. So what does that tell us? So wait a minute, or f prime. Remember, if the first derivative is positive, what does that tell us about the function? It's increasing. And then it changes to negative. What does a negative first derivative mean? Decreasing. So if you go from increasing to decreasing, in other words, first derivative positive to first derivative negative, okay, we have a local maximum, okay? Then there is a local maximum at x equals a, okay? And it says if f prime at a is equal to 0 and if the derivative changes from negative to positive at x equals a. So in other words, the derivative goes from less than 0 and here to greater than 0. Then what do we have? If we're going from decreasing to increasing, we have a local minimum, okay? Then there is a local minimum at x equals a, okay? And if f prime at a is equal to 0, but the sign does not change, okay, then no local extremum. Max or min. Okay. And this essentially is the first derivative test. Okay. So let's do a quick example, and then I'll give you a couple of examples to work on. Okay. Let's say our function is x e to the x. Okay. What am I going to have to use to find the derivative? Let's see if let's get some different people in. Come on. There's a lot of you there. Let's not all be so quiet. I know on these online classes, it's very easy to just stay quiet, but trust me, it is a little less boring when you participate. There we go. So you have to use the product rule. Perfect. Okay. So derivative of x is 1 times e to the x. Okay. Plus the first function, x, times the derivative of the second function, e to the x. And what do we want to do with this derivative now? If we want to find the intervals of increase or decrease and find the max and min, what's the first thing we want to do? What are going to be the key values that are going to help us determine this?
Make everything to 0.
There you go. Make your derivative equal to 0. Okay. Now, of course, here to solve this, you're going to have to use some algebra. What do we notice about these two expressions? Actually, I think we might have even done this one earlier. What do we notice here? What's going to help us?
Factor out the e to the x.
There you go. Factor out the e to the x, and left 1 plus x equals 0. And can e to the x ever be 0? Yes, no, maybe? E to the x. Remember, it's an exponential function. Are those ever equal to 0? This is never equal to 0, but 1 plus x can be equal to 0. X equals -1. Okay. So the only place where we can find a maximum or minimum is at x equals -1. Okay. So I'm not sure how you folks, there you go. That's what we call a critical point. Okay. This is what we call a critical point. Okay. But that just goes to show how important maxes and mins are in solving problems. That's a pretty, it's a pretty dramatic name to call something a critical point. Now, I'm not sure how you set this up. There's different ways you can set it up. I'll show you what I do just because I think it's, there you go. We're going to use a sign chart, but you're going to see I'm not even going to use a chart. I'm going to even simplify it. I'm going to use a number line, okay? Because a chart just takes me too long to write, okay? And what I'm going to do is I'm interested in testing the sign of the derivative, okay? So here, the only place this derivative can change sign is at the x-intercept, okay? It can't change sign anywhere else. Let's think about where a function can change sign, okay? It can change sign at a intercept. It can change sign at a vertical asymptote. I don't have any vertical asymptotes, okay? That's really the only places can change sign. There you go, changes sign there at a 0. Now, let's remember, does it have to change sign at an x-intercept? Does a function have to change sign if it has an x-intercept? No, exactly, because it could do something like this, be 0, but then go back up, okay? And remember what we said, just because we have a critical point doesn't mean there has to be. And so what I do here is I put this -1 and I test a number to the left of -1, say -2. I test a number to the right of -1, say 0, and I just find the sign, okay? So here, if we put in -2, e to the -2, e to the x is always positive, so that's always positive. 1 plus -2, oh, that's negative, okay? Let's put 0. Again, e to the 0 is positive, 1 plus 0 positive, there you go, positive. So what is this telling me? This tells me that the function is increasing on, well, all values to the right of -1. Okay, so from -1 to positive infinity. And where is this function decreasing? Well, for all values to the left of -1, because the derivative is always negative to the left of that. So from negative infinity to -1. Okay, so if they're asking you for intervals of increase or decrease, you just look for where the derivative is negative, where the derivative is positive. And if you're looking for local maxes and mins, well, here, what are we going to have at -1? If it's changing from to negative to positive, we look at our first derivative test, and it says if the derivative is 0 and it changes from negative to positive, then we have a local minimum. So we have a local minimum at x equals -1. And what do I do if I want the actual y value? What am I going to do if I want the actual y value? Who's going to tell me that? Where do I put this -1? For x, in the derivative or in the function? Yeah, for y, exactly. You put it
In the
back into the original function, okay? Because the derivative gives you the rate of change. You don't want the rate of change. You already know that's equal to 0 there, what you're looking for. So now, so y would be -1 times e to the -1. Whoops, e to the -1. So hey, we saw that before. -1 over e. Okay, there you go. So are we okay with finding maxes and mins? Do we have any questions on this? Or should I just give you another example now? Perfect. Easy. Do you want another example before we move on to the other stuff? Yeah. Okay. So let's give you. All right. So a sort of similar question, but made it a little more complicated. So what I want you to do is I want you to find the intervals of increase or decrease, and I want you to find the maximum and minimum if there are any. Okay. So let me give you maybe 5 minutes to solve that. And let me know if you have any questions. Let me just check the chat. I haven't looked in a while. Okay. Okay, folks, so maybe another 30 seconds and we'll start taking this up. All right, so let's take a look at this here. And what you're going to see is that all the steps that we're doing, these are all the things that are going to lead to eventually being able to sketch curves, number one, okay, which is, I think, the main thing that's going to be happening in this unit. But then in the next unit, you're actually going to see how you can use very similar method to solve problems where you're looking for the max and min. Okay, you're looking for like the best case scenario in a situation, and usually the best case scenario means either having the most of something, so the most money, or having the least of something, so let's say the least cost. Okay, so here you just follow the algorithm. So it says take the derivative, so I'm going to have to find the the product rule. So take the derivative of the first function. Okay. But what am I going to have to use to take the derivative of e to the 2x? Who's going to remind me what I'm going to need to use? Because before I just had e to the x, but now I have e to the 2x. So what am I going to have to use here? Anybody?
Chain rule.
Exactly. So this is where we see that the chain rule comes into play. Now, the reality is the chain rule that chain rules you're going to be using to solve, these are probably going to be way simpler than the ones we did before, but it's good to practice those harder ones. So when you have to do an easy one, you don't make a mistake. So the derivative of e to the u is e to the u. But now let's take the derivative of the inside function 2x. What's the derivative of the function 2x? Just 2. Okay. So that's the derivative of the first function times the second function. Okay. And plus the first function, e to the 2x, okay, times the derivative of the second function, which is just 2x minus 0, so 2x. Okay. And now I want to set this equal to 0, but I'm going to have to do some algebra. So here, let's see. Look at that. I have an e to the 2x, which is common to both. So I'm going to take that out. And let's see what we're left with here. Well, we're left with the 2x squared, okay, minus 2, okay? And then here, what are we left with? We're left with the 2x, okay? And so now, let's clean this up a bit. So can we see something else that we can factor out? All right, might as well factor out the 2, make our lives easier. Okay, so what are we left with? We're left with x squared plus x minus 1, okay, equals 0. And now we're going to have to solve this. Okay, so the first thing I notice is that this is never equal to 0 as before, so I don't have to worry about that. So the only thing I have to solve is x squared plus x minus 1 equals 0. Okay, and I guess this is the problem when you pick an example without checking it first. Is what's the problem? Is this going to factor? It's not going to factor. So what are we going to have to use here if we want to
Even if you use the quadratic formula, it doesn't give you nice numbers.
Oh yeah, no, it's definitely not going to give us nice numbers, but hey, you have to imagine, if you're solving a real life problem, very rarely is it going to be x equals 3. It's usually probably going to be x is approximately equal to 3.21. So yeah, we're not going to be scared of quadratic formula. We'll just use it. So here x is equal to, hold on, somebody's trying to get in. Okay. Let's just do it. That's fine. So negative b, so -1 plus or minus square root of b squared. So 1 minus 4 times a, which is 1, times c, which is -1. Okay, all over 2. So what does that give us? -1 plus or minus 1 plus 4 is 5. over root 2. Okay? Now, because I didn't actually ask you to apply this to length or distance or time, you should be giving your answer in exact values. But when I'm testing my intervals, this is not an obvious number to me, so it's definitely a good idea to approximate that. So let's approximate that here, and you can do it. I'd really appreciate it if people do this with me in case I make a silly mistake. You're gonna correct me. So -1 plus root 5 divided by 2. So that's about 0.62. And the second one, let's do -1 minus root 5. Okay, divided by 2. Okay, is about -1.62. Okay, so now when I test my interval for my derivative, I have to put two numbers on here. Okay, -1.62 and 0.62. And so now I can test my intervals. But I'm going to show you a trick here, because I could choose numbers and stick them into my derivative. But remember what we said? Can this first part ever be equal to 0? No. In fact, what can you tell me about 2 times e to the 2x? You should be able to tell me something about that number, regardless of what x is. Doesn't matter whether x is 1 or 3 or -500. Is there something you can tell me about this expression, 2 times e to the 2x? You see that this is always positive, okay, because it's just an exponential function. So if I'm looking for the sign, all I have to do is look at the quadratic. But here, it's a quadratic and the leading coefficient is 1. In other words, I don't really care that it's 1, but I care that it's positive. And what do we know about a quadratic that has a positive leading coefficient? It opens upwards. Okay, can you see that this parabola, because it opens upwards, would look something like this going through the x-intercepts? And so I don't actually have to test the intervals by sticking numbers in here. I know it's going to go from positive to negative to positive. Okay, is everybody okay with that trick I just used? You see it saves me a lot of time. Okay, good. All right, so now let's start answering our questions. When is this increasing? Okay, well, it's increasing from -infinity all the way to, well, remember, I don't want to use the approximated answer. I want to use the exact answer. So -1 minus root 5 over 2. Okay, and it's also increasing in that interval from -1 plus root 5 over 2 to positive infinity. Okay, when is it decreasing? Well, it's decreasing in between those two numbers. So it's decreasing from -1 minus root 5 over 2 to -1 plus root 5 over 2. Okay, and lastly, are there any local maxes and minimums? Yeah, here, what would it be? You realize the derivative is going from positive to negative. So the function is going from increasing to decreasing. So you're going to have a local maximum. Okay, and here the derivative is changing from negative to positive. So that means the function is going from decreasing to increasing. Okay, and so that means at this number here, we have a local minimum. So we have a local minimum at x equals -1 plus root 5 over 2. Okay. And if you wanted the y value, you'd have to stick it into the equation, but I don't think we're going to waste our time doing that. Okay. And if you put this into Desmos, you will see that these are indeed the points, these important points on your function occur at these x values, and you should see where the function is increasing and decreasing. And eventually, you're going to find this information and start to put together a case for how to graph the function yourself. All right? Okay. Any questions we have on this here that we want to ask in terms of the process? So this one here, quite a bit of work because we had to take the derivative. We had to solve for when it was equal to 0. It happened to not be nice numbers for your x-intercepts. That was fine. We created our number line or our chart. You use whatever you prefer. You can create a chart or use the number line to determine where it was increasing, to determine where it's decreasing. And then we use that information to determine where we have local maxima and where we have local minima. Okay. Any questions on this?
Could you
No. Yeah.
Could you please explain your trick one more time, please?
Yeah. So here, in the end, what am I trying to determine? I'm trying to determine what the sign of the derivative is in each of these intervals. Now, since these are the only x-intercepts, these are the only places it can change sign. Okay. So one thing you can do is pick a number in each of these intervals. Say here I could take -2, put it in my derivative, and see if my derivative is positive or negative. Then here, pick say 0. Any number between these two, stick it in my derivative and see if it's positive or negative. And same thing, pick say x equals 1, stick it in my derivative and see if it's positive or negative. So that's always an option. Okay. But what I noticed is that the derivative is made up of this product of these two expressions, right? And the first part of the product is something that's always positive, okay? E to the 2x is always positive because e to the 2x is just an exponential function that's always bigger than 0. And of course, 2 is a positive number. So can you see that this expression is always positive, okay? Which means that whenever the inside of the bracket is positive, the derivative is going to be positive, and whenever the inside of the bracket is negative, the whole thing is going to be negative. So does that make sense?
Yeah, that makes perfect sense. Thank you.
Perfect. But that's when I noticed, what is this thing inside of the bracket? It's just a parabola, and because the leading coefficient is positive, it's a parabola that has to open upwards. So I already found the x-intercepts of that parabola. That's what I found here. And since the parabola has to open upwards, I know the parabola is going to look like this. It's going to start positive, then at the x-intercept, it's going to go negative and then come back up and go positive. So you see how I'm only working with this part of the derivative. Now this only works because I know that this part is positive all the time. So I just need to look at the sign of the quadratic portion of that derivative. And since I know it happens to be a parabola that opens upwards, I know it has to go from positive to negative to positive. Okay? And it's a quick way of showing the sign of the derivative without having to take a number, stick it in my expression, possibly make a mistake on my calculator, So now, does this work? If this was a cubic, would this be easy to do? No, unless I had the x. If I had the x-intercepts, yes, it would be. Okay, so it all depends on the type of function that you have there. Okay, so it's one of those things. If you don't notice it, you can always use the method of just inputting a value in each interval. But if you happen to notice that one portion is always positive, or say always negative, and then the other portion can be graphed really easily, then this saves you a lot of time. Saves you a lot of, like I say, just putting something into the calculator. Okay?
Thank you.
Okay, great. So I'm looking at the time and I'm thinking maybe Like there's no point in starting something new. So I just want to sort of recap that. So for now, well, chain rule. I mean, obviously we had to use it anyway. So we've done the chain rule. We've looked at increasing and decreasing functions. We've looked at local maxes and minimums. So now we're going to go into the next sort of characteristic of a function that we can get using the derivatives. So that's what's coming up after the break. Okay. So let's give you a couple of extra minutes. Let's just start again at 7:45, but we'll start again at 7:45 sharp. Okay. All right. Okay, so I'm actually going to stop the recording now just so that it doesn't get too big, and I'll, later on I'll post these. All right, so